in Altair, India. So I'll take you through the solver, CFD solver of Altair, which is called as AccuSolve. So I would just showcase a minimum requirement. This is a demo problem pipe flow. So you just have a look at it. So this is the pre-processing part of AccuSolve, which is a CFD solver. So this is the main part basically. So you will be doing means importing the geometry, doing the mesh, sorry, applying the boundary conditions, everything else in this pre-processing part, which is called as AccuConsole. Okay. So I'll just create a new file called pipe. Just save it. Okay, so file, import. I'm importing the parasolid file, which is a geometry. So these are all import options you have. It is able to read fluent mesh, it is able to read parasolid file, ASYS file, ProE part file, ProE assembly file, CATIA part file, CATIA assembly file, etc. Okay, so we will read directly the geometry parasolid file. Just say OK. So this is a pipe which has been imported in AccuConsole. So right now, if you go to models, volumes, and surfaces, okay. So this default option comes up with the red color circle. It means that it is empty, nothing has been there. So you can right click on model and say purge. So all your empty surfaces and volumes should be deleted. Okay. So you have a pipe here. So the objective of the simulation is to make sure that we do a CFD analysis of a pipe. So water is flowing in the pipe with inlet, say a certain mass flux or something. So basically how the flow is actually flowing. Okay, and basically to see the velocity, the pressure drop of the system. Okay, so right now for doing the CFD analysis, we need to make sure that we have an inlet and outlet of a pipe and the wall basically, which governs the surface, basically bounding of the pipe. Okay, so I create two new surfaces, right click, say new, right click, say new. Okay, so I rename this as inlet, I rename this as outlet, and I rename this as wall. This inlet any questions you have, you can just type in on the chat window, please. Okay, so what I do here right now is I have to assign these surfaces over the inlet and outlet. So let this be by inlet face. So right click on inlet, say add to, select this face and say done. Similarly for outlet, right click, say add to, select this face and say done. Okay, so inlet simple boundary condition is inflow. So let me give us mass flux, any boundary conditions you give. So basically inlet is assigned a mass flow rate with 2 kg per second, water is flowing at 2 kg per second. I'm really sorry. So go to outlet, change it to outflow, and wall is wall basically. Okay, so now over the surfaces in CFD, in any this one, we apply boundary conditions only to the surfaces. Okay, and to the volume we define what medium it is. Basically it is a fluid medium or a solid medium. Okay, so what we have done is inlet, we have given the boundary condition water. We have not said water, but basically inflow, basically whatever fluid it will be flowing at 2 kg per second. Your outlet is outflow, which is pressure outlet, and this is velocity inlet, and this is wall, your bounding of the pipe. Okay, so I can rename this as water. So basically if you see, it's very simple model, it's just a pipe. So this is my fluid medium, there's only one fluid and there's only one volume basically. So here the default is normally set it as air, so change it to water. Okay, so this is my fluid medium and my material model is water. Okay, so if you want to have a look at the properties of water, you can go to material model, say water. Okay, double click on water. So density, specific heat, viscosity, conductivity, viscoelasticity, everything is normally assigned to it. Okay, so this is how the properties of water takes place. Means the solver takes the property of water. If suppose you want to have many more material models, so basically the default material is air, aluminum and water. If you want something else other than this, you can go to tools, material models. Okay, so if you go to tools, material and models, you have a library of materials. So you can just click and say import, it will be reflected over your material model thing. So you have lots and lots of materials here, and basically if you want a particular material where even the material model library doesn't have, you can create your own material model. Right click, say new material model, you can rename, you can give your own properties, and you can assign it to your respective volume. Okay, now what I have given is my volume is water, my surface is basically inlet outlet. So what I'll do, I'll on one by one. So basically this is my inlet face. Okay, so this is my inlet phase. I give a simple boundary condition of mass flux with 2 kg per second. So water is going to flow from this surface at 2 kg per second. This is my outlet. The red part is my outlet, and I have given only outflow boundary condition. So pressure is normally 0. Basically it takes atmospheric pressure if you assign 0 here. Okay, and this is my wall. Okay, so wall is nothing but wall boundary condition. Nothing, very simple boundary condition. Just say water is flowing at 2 kg per second. That's it. Outflow is outflow. Okay. Now, problem description. If you go, it is a steady state analysis. The flow equation is Navier-Stokes equation. Turbulence equation, you can change it to laminar or Spalart-Almaris. It's your wish, basically. So laminar, you need to make sure that it's a laminar flow. Basically the recirculation of water and any other fluid material doesn't take place. It goes straight, the path is straight, but we cannot say that it is straight. So it's always better we change it to Spalart-Almaris. For a pipe, you can always give it as a laminar, no problem. Okay, because the flow is anyway going to be straight. Okay. Laminar auto solution strategy, if you see, maximum time steps of 100 and a convergence tolerance of 0.001. The convergence tolerance here means 0.001 means that your pressure and velocity values, it runs for different time steps, right? Different iterations. So if say suppose it has run for 15 time steps and stopped, it means that the 14th and 15th time step, the results of pressure velocity, the pressure difference between the results is basically 0.001 and it will stop. Okay, so if it doesn't stop automatically, it will run till a maximum of 100 time step. Okay, So now now comes the most important part, the meshing. So click on MSH on the left hand side. So all your meshing parameters would be activated. So normally it is in 0.1. It's in meters, okay. So you can give it as some value 0.03, and you can do the volume meshing. If you see here, generate mesh, or you can go to tools, generate mesh. Okay, say okay. So it has meshed it. So I will, and display type, you can change it to solid and via. Display type, you can change it to solid and via. So basically this is the mesh generated, and you can launch OcuSolve with this arrow. So just click on here and say launch. So basically your simulation has run. So it has run a total time steps of 16, okay, and it has stopped automatically, and stop, end time step. So now you need to do your convergence. Basically you have to look at your convergence, which is the most important part in any CFD simulation. So we have something called Apoorv. Okay, just click on this Apoorv, go to residual ratio, final, right click, pressure plot, velocity plot. So if you can see my screen, um, it has run for 16 time steps. This is pressure, this is velocity, and we have given a convergence shortness of 0.001, and you can see well below the mark the solution is basically steady. So it has run till 16 time step and stop. Okay, so convergence of the simulation has been achieved. Okay, so this is how you come to a conclusion that the convergence of the solution have been achieved. Okay, now let's go to the post-processing part. Just click on field view, launch AccuField View Visualizer. Just click and say okay. Okay, so you can actually plot your pressure and velocity over here. Okay, similarly, if you want to plot your coordinate surface, basically what you can do is you can change it to geometric, change it here, you can make it transparent. Okay, go to your coordinate surface, say create, you can change it to scalar, you can change it to constant. So basically this is pressure. If you want to check for velocity, you can actually check. So if you can see here right now, you can change it to local, you can change it to legend, basically. So this is your velocity magnitude. You can change it in, you can cut the section in any of the coordinate plane. So Y, Z. Okay, so you can measure the boundary surface, basically the surface of the pipe. You can plot the pressure velocity over a coordinate section. Also you can plot the same thing. Okay, now let us see, you have a different requirement. Say you have a boundary surface, you need to create one more inlet, say okay, put scalar, sorry, okay, change the percentage to 0. So basically this is my inlet face. Okay, and this is my pipe. Actually the view is in perspective mode. Okay, so this is my pipe actually. If you can see. Okay, now you want to visualize what is the flow. What you can do is you can go to streamlines, seed a surface, make it 1000, select this surface and say OK and say calculate. Okay, you can change it to scalar, and if you can see the flow, you can actually visualize. Now the best part is growing, so you can actually animate it. You can see how the flow has been developed. So you have a lot of options, say spheres and lines. You have spheres, how the flow is actually going over the pipe basically. So say a line of spheres, so basically you can see how the flow is actually flowing over that pipe completely. Okay, so this is field view where you can do the post processing of your CFD stuffs. So console is the preprocessor where we had set up all our boundary conditions, and we have meshed the model. So console is the preprocessor. Apoorv is Apoorv. I have already shown. This is a convergence residual viewer. Okay, and then field view is the post processor. You can you can actually visualize how the flow is flowing. Basically coordinate surface, you can measure the pressure, velocity at different sections, and basically you can do the post processing completely in field view. So these are the Altair CFD offerings. So this is why I did this pipe is to basically tell you how the simulation of a CFD simulation, basically it's a very small model simulation occurs. So let me quickly go ahead and concentrate on the CFD part for aerodynamics. Okay, so let me give you a small intro. So any questions you can just type in, and I'll solve your questions over the meeting. So let me take a step ahead and go with external aerodynamics with Altair with HyperWorks basically. So I am Kamleshwar. So basically I work as a CFD specialist with Altair. Let me take you through an example, basically overview of external aerodynamics. I'll try to finish it within the limited times. A live demo of how to do an aerodynamic simulation. I'll take a simple car model, a symmetric model, or not a symmetric model, basically a car model, and how to solve, what are the options you should look after, and how to make sure that you do a complete aerodynamic simulation of a car using AccuSolve. Okay, and then I'll have a live demo. Basically, I'll be doing it. So the pre-processing tools would be HM, that is Hypermesh, and AccuConsole. I have already shown you how AccuConsole, AccuSolve, AccuProbe, and AccuFieldView works. Okay, so solving is basically AccuSolve, which you will not be able to see. You just run it, then you can do basically your post-processing stuffs there. Okay, so what are the importance of external aerodynamics normally? So why do we do aerodynamic analysis using softwares? So this is just only for your eyes. So basically what we look after is the performance, the performance the performance of your vehicle. The aerodynamics is a major importance in determining the performance of your vehicle, basically your car, basically anything which is moving. Okay, so how this aerodynamics would help in increasing the performance of your vehicle? So basically the fuel economy, the emission, that's why emission exhaust system also plays an important role. If your exhaust system doesn't work properly, all your exhaust gases would be reflected back to your engine, and your performance of your engine would be affected hugely. So the emissions should go out of the exhaust systems. properly, making way that all your gases, harmful gases, are removed from your vehicle, so that it doesn't affect your performance of your car or any vehicle. And basically acceleration, maximum speed acceleration, what time you press, what speed are you going. So basically for different speed and different yaw angles, the aerodynamics of a drag or lift changes. And there are different other reasons for aerodynamic analysis as well, say cooling, stability, comfort, and visibility. Okay. We look mainly for two forces during the aerodynamic simulation. One is downforce and drag force. Downforce and drag force. So basically the drag force would make sure that your vehicle is affected by the wind load, and your lift force is something which would lift your car, and basically there will be a rollover of your car or something like that. So basically both the forces should be minimum. Then we have something called aeroacoustics. So right now this I'll not concentrate on the aeroacoustics part, because I'll concentrate only on the aerodynamics part. Okay. So basically what is drag force? Drag force is due to the opposite to the direction of the motion of your car. If your car is moving say 50 kilometers per hour, there would be wind load acting on your car, so which is acting in a motion, which is your car is in motion, which is in direction opposite to it. So it accounts for 75% of the car's resistance, that is 100 kilometer per hour. Say if you drive at 100 kilometer per hour. So how do you compute this frontal area of the basically how do you compute your drag forces? So drag force is this formula. So half rho v square. Rho is the density, v is the velocity, and CD is your car shape, basically your coefficient of drag. It will be determined by your solver, and A is the frontal area of your vehicle. So basically the wind load touches your frontal area of your car, basically your bumper, your windshield, etc. So that frontal area you need to calculate, okay, and you need to supply this frontal area calculations to your computation. So Ft is your drag force, rho is the density of your fluid, basically density of air, v is the velocity at which the car is moving, CD is the drag coefficient of drag, basically it will be given to you by the solver. Then A is the frontal area of the vehicle. Okay. Drag reduction by minimizing coefficient of drag, optimization. So a lot of automotive companies do the shape optimization of the car to making sure that drag is reduced. Then comes the lift force. This is perpendicular to the street, impacts steering behavior. It definitely impacts your steering behavior. This is mainly for race cars, which would need more grip. If you have seen your Formula car racing and all, Formula 1 and all, there are more chances of your car to roll over. Okay, so how does this rollover happens? Through the lift force. This is because of the lift force. So this is an example. Running and suddenly means basically you drive the car at say 100, 150 kilometers per hour, and the wind is so much that it lifts your cars and make sure that it rollovers. So these are the two forces which are very, very important aerodynamic forces. Okay. Side force. So basically perpendicular to the direction of the motion, and sensitivity towards the side of the wind gas, basically of the car. Okay. So this is the drag resistance versus the rolling resistance. Okay, say at 70 kilometer per hour, the aero resistance is dominant. So you do certain types of resistance analysis. Say you do basically say some force with the velocity, and you can plot what is the drag resistance, that is basically what is the rolling resistance. So these are the early shape optimizations. So basically if you see the older cars, they were at certain shapes, and this what they used to do was to make sure that the drag is minimized, and they used to do it. So basically they changed a lot of shape optimizations over the car, so making sure that the drag and lift forces are minimum. So normally, if you see, there were a lot of common trailing edges where two aerofoils were used, making sure that the drag was minimized. So this is a Porsche 911 1995 car model. So where the drag coefficient of drag was determined as 0.33. Okay. Then this is your history of aerodynamic drag. So this is just an example of how your drag force normally changes. So if you can see here, this is a BMW car, BMW, Mercedes, Honda. So they the drag comes between a zero point 0.2 and zero point 0.3. So it's around 0.25, 0.28 or something like that. So if you can see Honda, then you can see a lot of cars, other cars, Centurion, Chrysler. So these are the drag for different cars, and basically for the number of years. Okay. Not only for the vehicle, even for any structure standing where the wind is acting and making sure that the drag is lift, and of course, for aeroplanes, passenger aircrafts, literally passenger aircrafts or war aeroplanes, the drag plays an important role. So if you can see, the drag is 0.031 for the Boeing aircraft. For Eiffel Tower, which is standing tall, and basically the wind is acting at a much larger place because static structure. So you can see the drag of that tower is basically 1.8 to 2. Then even for the man running, walking over the distance, and basically the air flow over the body, it will be around 1 to 1.3. Let's come to a source of drag on a passenger car. Okay, so on a passenger car, if you see, the tires utilize for 30% of the drag, sorry, 25% of the drag. The basic model, your shape of the car, down shape of the car gives 30%, and basically the top end of your car gives 45%. Okay, so this is wheel deformation, how the wheel deformation occurs, how the wheel deformations over the aerodynamics occurs, and how do we do it while we do it the meshing part. Then aero wheels reduce overall, so you can see it, how the frame over the wheels, basically rim wheels, wheel frame, and they contribute to a large part of the drag. So how these aspects of rim design is done to basically make sure that your drag and brake cooling performance are quite good. Okay, so this is experimental wind tunnel. So this is how a normal experimental testing, aerodynamic testing of a car takes place. So they calculate what type of wind load is acting over the car, and how your software results basically matches with your experimental results. Okay. Then comes two common techniques, that is rapid prototyping and clay car models, because it's very difficult for ready-made car to come. So they create a rapid prototype of the same size, because it doesn't matter, because the shape of the car needs to be maintained, and they check how well your car is resistive to the wind load. Okay. Normally, this is just for a Formula race car. I have just prepared for the Formula race car, so don't go on the timings. Preparation normally takes around 4 weeks to clean up the surface of a car, surface meshing, because normally the geometry given is very bad. So around 4 to 7 million elements. Then volume meshing around, you can make it till 15 to 25 million should be good enough. Then make sure that you have 5 to 10 boundaries. I'll do the demo. So I can tell you, but I'll not do the meshing because the meshing would take time. But I'll set up the every condition and I'll show you the results as well. Okay, so then CFD run. So don't go on the course. This is just an example. And basically it will run a night, basically 10 hours to 15 hours runtime would be there. Then post processing we'll be using a Q field view. Okay, this is for a Formula race car where the R&D develop is so much that they use so much of heavy elements and post processing data. Okay, so for you, don't worry about all these details. You will be using a small computer. Modeling aspects, surface mesh. Make sure that your outer part of your car you capture very properly, because if you don't capture your outer part surface of the car where the wind is gonna hit, the frontal area of the car would change, which would which would actually be incorporated into the drag formula. So if your frontal area changes, your drag value changes. Okay, so make sure that you capture your geometry very nice. Then comes the volume mesh. Around 2 to 3 refinement zones of the meshes are required. I'll tell you how to do these refinement zones in Q console. Then comes the boundary layer, minimum 5 to 10 boundary layers over the outer surface of your car. Then wheel modeling, don't go much, I'll not go much on the wheel modeling part right now because just a simple car. So I'll skip this part. So I'll come to the summary because the time is just till 1 o'clock. The aerodynamics plays an important role. I already showed you how the cooling, performance, comfort, stability, and visibility would come. Then history of aerodynamic of different cars we have seen, and contribution to drag. Basically for the car, also I have shown you how much percentage of the outer surface of the car would account to your drag force. Then wind tunnel experiments, how it is done, and CFD for external aero modeling aspects. So your 70% of your time goes on the modeling part, that is the meshing. Very important for an aerodynamic analysis. If your meshing is perfect, your results would be perfect. Okay, so I'll just go directly. So I think this is the model given for the student this concept. I'll take the same car. The modeling aspects I'll tell you. Okay. So what I'll do is I'll go to hypermesh. I have already done surface meshing. Okay, so I have built a small wind tunnel, and basically the most important part is building of the wind tunnel. Okay, just hold on. I can share this PDF file if you are interested. Just let me know. See, this is how you should build your wind tunnel. Okay, if you are participating, we will check all these things. So this is how you should basically wind the tunnel. You can Google it how you need to model the wind tunnel, and you will almost receive the same part. So basically, length of your car, the inlet should be 2L, the outlet should be 4L, and height and width. So just make note of it. So make sure that you build your wind tunnel accordingly. Okay. So this is the standard dimensions of doing the aerodynamic CFD analysis over any software. Okay, so basically you need to build your wind tunnel something like this. Okay, then so this aerodynamic analysis is done by Mahindra for a truck called Navistar. You might have seen it over the highways, big truck. So they have used Accusol for aerodynamic analysis of the truck. So if you can see, these are some results, and this file you can get it from the Altair website. You just go there and type Accusol. You can get hold of these papers. Okay. Next comes, so I have just for the demo purpose, I have just built this wind tunnel. Why I have built this wind tunnel small is because I need to get it in Docker console, and basically this is an online meeting. So make sure you build the wind tunnel according to this dimension. This is most important part for doing a CFD analysis. Building of a wind tunnel, how do you end up build a wind tunnel accordingly? Okay, so make sure you do this. Then, sorry, I'll go to hypermesh. So this is the meshing I have done. So this is a okay mesh. So you can still refine it. What I'll do is I'll just show you the car. No compromise on capturing the surface of the car. Okay, no compromise. Okay, so basically this would go and affect your drag. So basically you have to make sure that you capture your car exactly the way it is. Okay, next important thing is wheels are grounded, your tires are grounded, so you have to make sure that you model your car exactly as it is grounded, something like this. Okay, so this is a small approximation what we take. So make sure that your car is grounded over the surface of it, surface of the wind tunnel. Okay, so it is grounded. If you can see, if you can see something like this. So I have made sure that the tires are flat over the ground. Okay. Now this is my, okay, I'll on one by one. Okay. So this is my car. Okay. This is my inlet of wind tunnel. So basically the airflow would be given at this inlet at whatever speed your car is moving. Then comes the outlet. Okay, your inlet, your outlet, and these are your walls. So basically 4. Okay, make sure that you do your scaling and put it in meters. Okay. Okay, so this is in meters just to show. Make sure you do your scaling. So go to tools if you want to see the scaling, tools, scale, change this to elements and make sure that you do the scaling. You have to make sure that your model is in meters. Okay, because Accu console will read only in SI units, and basically hypermesh is dimensionless software. So basically whatever dimension you give in hypermesh, you need to maintain it, then only it will take. So make sure that it is in meters. There are 100% possibility that your model is in mm. So just select all the elements, scale it accordingly and change it to meters. Then change your profile to CFD, CFD Accusolve, say OK. Okay. Then export it in Nastran format, CFD. You can change it to Nastran format, any format, and export it. I have already done the export, so I have it will save it in .nas file. Now what we will do is we will import this NAS file into Accu console. Okay, I'll create a new file. I'll close this. So you can create a new file here. Say just car. Just save. Okay. So file, import. This is your Nastran surface mesh. Say open. Okay. Now the most important part here is you select by volume regions. It will detect the volumes automatically. Surface grouping option by attributes, HM name comp. So whatever you name, give your name here in HM. Basically your car, walls, inlet, outlet. Okay. It means that the same name with the surfaces would come. Okay. Say okay. It will take some time to import it. Okay, so it has come. So if you can go to see to models and surfaces, car, inlet, outlet, wall. So basically you can say purge. So whatever the name you have given here, car, walls, inlet, outlet, the respective components would be read automatically here. So you save a lot of time in the pre-processing when you do it in HM. Okay, so now if you see, this is my car. So basically you can retain the same mesh as well. That's why we do the meshing there. So you can say display type solid and wire. So you can see the same mesh over the surface of your car. Okay. So I'll just say display type solid. Okay. Now this is your car, your inlet, your outlet. Okay. And basically the walls surrounding. Okay. Now we need to give some boundary conditions for it. Oh, okay. Most important part, what I'll say display of volumes. Volume 1 is your wind tunnel. I'll make it transparent. Right click on the volumes and say transparency on. You can see the outer surface of the car and the wind tunnel, and you off it and only the car. Okay, so this is how your volumes get detected automatically in Accu console. So that is that helps you a lot while you do your setup for the aerodynamic analysis. Okay. Now you can rename it. This is your fluid region basically, and volume 2 is your car. Okay. Now we will set up certain boundary conditions. So problem description. This is a car problem. This is a aerodynamic simulation. So this is a steady state analysis. This is a Navier-Stokes equation. Then turbulence, change it to Spalart-Almaraz. So we have a lot of turbulence model. Each turbulence model is being used for different applications. Okay. So for aerodynamic analysis, Spalart-Almaraz is good enough. You can use Spalart-Almaraz turbulence model. Then go to auto solution strategy. You can say how many time steps you want. It depends unless until your convergence is achieved. Okay, so maximum time steps given 100 and convergence tolerance is 0.001. Everything in default. You can run it for more than 500 time steps also. So it depends on the user and how do you arrive whether the solution has converged or not. I already told you, I'm not going to tell you on this part again. So you have to make sure that whatever CFD solution you get is converged. Okay. Next comes the nodal initial condition. Nodal initial condition means solving the simulations. You to take some initial conditions. Okay, say suppose you are doing a temperature simulation. So I have not on the temperature part here. So if you want to do a temperature simulation, you need to make sure that you give your ambient temperature, because normally what you want to do a temperature simulation, ambient temperature is some room temperature you need to give, right? So that you can give it here. Say suppose you want the pressure to be initialized from the nodal initial condition, you can give it here. So normally for Spalart-Elmares turbulence model, we need to initialize the eddy viscosity. Eddy viscosity plays an important part in solving the Navier-Stokes equation. Okay, so we initialize it at a very lower rate. Okay, let it do it on its own. I give it value slightly greater than means almost 0, that is 0.00001. Okay, 1 e power minus 5 I have given to initialize the eddy viscosity. Okay, the setup is very simple. Fluid is you, and one more thing is, and I'm not going to speak much because this is you can do a, if the car is a symmetric model, you can still do a symmetric CFD analysis as well. So cut the car half, make sure you build the wind tunnel accordingly and do the analysis. And basically while doing post processing, you can always use the mirror option. Okay, so fluid is my air domain. Fluid is my air domain. Car is not air domain. Basically, this is a solid part. So make sure you give it as solid. Okay. Anyway, it doesn't matter. We are not going to give any mental model because we are not going to mesh inside the car. Okay. So I will say no mesh. So this volume will be automatically deleted. I'll tell you how. Now giving the boundary condition: surfaces, car, wall. Exactly. So car, assuming that all windows are closed and everything else, so the air is not going to enter inside the car. So basically air is going to hit the outer part of the car and move away. Okay, so I have given it as wall. This is inlet boundary condition. So basically you have to make sure that how the inlet is placed. So this is my inlet face, right? So this is my inlet face, and what direction it is? Basically, it is in x direction. Okay. So simple boundary condition. You can give, oh sorry, inlet. You can give inflow, and velocity you can give it in x direction. Basically, at what speed you want the car to move in. Okay, say you want to move it in 20 meters per second or whatever the boundary condition is. Okay, or you want to move it in 50 meters per second. Okay, so you can give it directly here. Then outlet is your outflow. That's it. Okay, and basically all the other part which covers the bounding of the car is your wall, which is normally default wall only. Okay. So I'm going to show you once more. Okay. So this is your car. This is your inlet. This is your outlet, and this is your wall. So basically, we have given boundary conditions, something like your car is wall, your inlet is inflow, your outlet is outflow, your walls is walls. Okay. So inlet we give say 50 meters per second. Okay. So boundary conditions are very simple. The basic, most of the time, what you are gonna spend is on the meshing part. Okay. So click on MSH. So I'll make this as transparent. Okay. Now global mesh attributes. Click on MSH, then only all your meshing parameters, only the meshing parameters would be activated. Okay. So global mesh attributes. So basically, whatever value you give here, it will take the make sure that that would be the minimum value. Okay, and it will do the meshing here. Any questions you have? Any questions you have? Just type it on the chat window, because everyone is mute and no, I cannot hear you. So any questions you have in between, please, I encourage you to ask questions. So please type it on the window. Okay. Next comes um, relative message. I have already told you. So you can normally give it as 0.1. Then goes car. So car inside there is no mesh required, because the air is not going to go inside, right? The air is going to hit the surface of the car and it's going to spring out, right? So you need to make sure that you do not mesh it inside the car. So how to say no mesh? Basically, so click on this and change it to no mesh. Okay, so it will take that the volume mesh inside the car is not needed, so it will do only the volume mesh outside it. Okay, basically the wind tunnel. Now the most important part here is how to give boundary layers which will define you to how to create boundary layers over the car. Okay, so that's some fluctuation happening over the screen, I don't know. So just click on the car, boundary layer flag on. You can define how many boundary layers you want, say 5 or something. Then most important part here is how to make sure the air entering and hitting your car, the mesh should be very good, right? So you need to make sure that the refinement zones would help you create a much better finer mesh over the car. Okay, so you need to, on the zone mesh attributes, right click, say new. So zone mesh attributes, you can change it to box. Okay, so if you can see we need to make sure that we create a box over the car for the aerodynamic analysis. So you can change the box length, etc. So right now if you see, it's something like this. Okay, the red color is the box, so you can change it to 3. or you can make it to 5. Okay, then you can make the box length as 2. Okay, but only half the car is covered, so you can change it to 2, or you can make sure to 2.5, and this one I can change it to 1.5. And if you want to measure exactly below the wind tunnel, you can still make it to 1.2. Okay, no, it's coming out. So 1.3 is perfect. Okay, similarly, if you want to build one more attributes, you just say duplicate. Okay, just make sure that you give a bigger size over here, say 1.5. You can change it to 5.3, and the box length you can still increase it to 2.7. So basically there are two mesh refinement zones. So if you can see, and what I'll do, I'll on only the car. So only the car for the aerodynamic analysis. So if you can see, so I on the first zone attributes. Okay, see. Okay, and the second zone attributes also I on. So basically I'll keep the transparency on. So I would encourage you to have at least 2 mesh refinement zones over it. Okay, so basically I've just shown it to you. I'll not use this one. Okay, and so I'm actually deleting this because I need to mesh it right, so it will take some time. So I have deleted one mesh. So but when you do the analysis, you have to make sure that there are minimum 2 mesh zone refinements over your car. Okay, and this is your wind tunnel. So basically, so if you can see something like this. Okay, you can always mesh it. So just go and generate the mesh. You need to make sure that you give a very good global mesh attributes range, at least 2 mesh refinement zones over the wall of the car, minimum 5 to 10 boundary layers. Okay. So it is meshing. Okay, what we will do, we will, okay, it's refreshing. Okay, model type, what you can say is display via. You can say the display type as solid and via. Okay, so you can see the mesh now. What you can do is you can keep the zone mesh off. Okay, now if you want to see the cut plane of it, how it has done the mesh. See, there is no mesh inside the car. Okay, so if I zoom it, there are 5 boundary layers. If you can see the screen, there are 5 boundary layers. Minimum 5 to 10 boundary layers is needed over the surface of the car. Okay, and if you can see, only where you have made sure that the mesh zone refinement box is there, the mesh is fine. But after the mesh zone refinement, the size is very hugely, right? So you have to make sure that you do the meshing appropriately and don't use so coarse mesh. You have to make sure that you have a very fine mesh. Okay, so minimum, even you can build around 3 mesh zone refinements, making sure that your mesh is very good there. Okay, any questions? Okay, so after you have done the meshing, it's time to run the simulation. So I will not run the simulation because it will take some time. Uh, so it's around 1.8 million mesh. If you can see here, 18,93,000. So I will not encourage to run right now, but I do have certain results to showcase. What I can do is, I'll open Aki Field View. Okay, so if you can see, so my car comes. Okay, so you can change this to any color, whatever you want. Now this is my car. Now you want to see certain results. Say you want to see the cut section of, so if you can see exactly, this is your wind tunnel. Okay, so it is not a local plot. 1 minute, this is a local plot. So if you can see the results of this, this is your inlet. So basically the car gets hit by the wind, this one, and this is the wind load happening. So the pressure is exactly lower at where it hit the car frontal area. Okay, why is it so? Because the pressure would be higher at that point. If you can show the pressure to you on the same surface, if I show the pressure to you, see, this is stagnation pressure due to the static thing. So if you can see, the pressure is higher, the velocity is lower. See, now if you want to see, you can actually change it to 300. So you can actually see how the airflow over the car is getting changed right now. Okay, this is how the car velocity profile over the surface area gets changed. Okay, so most important part is your meshing. Okay, your contour plots will be directly affected because of your meshing. So make sure that you have at least 2 to 3 zone refinements. Then you do your meshing finer mesh, very good mesh. Minimum 5 to 10 boundary layers from your car surface. As I showed, I have used 5. So I would encourage you to use 10 also over the car surface, and then you do the meshing. Then you just set up the boundary condition setup is very simple for aerodynamic analysis. You just need to provide your inlet and make sure that you do your analysis. If you want to see the vector plot, you just change it to vector. So basically, the vector shows how it will be changing completely. The flow. So can you see? Okay. This is how the velocity profile of the wind changes when it hits the car. Similarly, you can plot for this. Let me plot for the car directly. So I don't want the mesh. So I want the scalar part. Let me plot the pressure. Okay, so these results are not good. Okay, this is just for demo purpose I'm using. You need to build a very good mesh so that the results are also good. But you can see how the car pressure is acting over the car, over the wheels. So the pressure is more at the frontal area of the car because the wind directly hits the frontal area of the vehicle. Okay. So you have to calculate the frontal area accordingly. That is basically length into width, and you need to assign your this one. So normally your CFD report should contain how your velocity profile, your pressure profile of a car, how the velocity profile changes with respect when it hits the car, something, and then most importantly your convergence. Okay, I'll open Apoorv. So just open your log file in the Apoorv. You can see your pressure and velocity profile converging, okay, below 0.001. But if you can see your velocity, I believe, yeah, velocity is not converged. Okay, I have stopped the run in between. So you have to make sure that you get your converged results. But your pressure values are converged, but your velocity values are below, are above 0.001 only. So you have to make sure that you get a converged solution from it. Okay. Next most important part is how to calculate the drag value, right? So I have shown you the formula for the drag. So this is the formula, right? You need to compute your drag. So basically CD, right? So it CD is equal to 0.5 into FT into density into V divided by A, right? So you need to make sure that you plot your drag. You create your uh, formula to make sure that you create your formula to make sure that you have your drag values computed. So you need to create a formula. Most importantly, here use a function. Okay, so click on here. You can type drag, and most importantly, this is only for demo purpose. Don't go on the results part. Okay, so drag. First, you need to compute what is your FD, that is drag force, is equal to, this is x velocity over the surface of the car. So surface output, we have something called surface output. Okay, so go to surface output, car, your x traction, right click on that, copy and paste. So your surface output is computed. Okay, then what is your area? A. Area, you need to make sure that you calculate it on your own. The frontal area of your car, because that is the calculation part. You need to make sure that you calculate the frontal area of your car. So let it be around 0.8 or something. Okay. Now you have to make sure that you write a formula for calculation of drag. So value is equal to f.5 into FD. Your FD is will be taken from here into rho, your density of air. So what is your density of air? So go to your material model, air density is 1.225. So 1.225, your velocity is 50 meters per second. 50 into 50, okay, into area is 0.8. You can say directly 0.8. Okay, no need of this. Say apply, close. Now you say don't plot none. So user function drag would be plot. You can say replot. So if you can say, so don't go on the results. Don't go on the results because I have not run the problem properly. This is just for a demo purpose. So your drag is around 518. So basically, don't go on it because I have not computed it much clearer while running. This is only for demo purpose. So this is how you need to calculate your drag. Okay. 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 That's a request. Can you please show the flow lines? I'll show it to you. So this is how you compute your drag. Okay. Then comes the flow path, right? So you can see this is your car. So you create a boundary surface, one more boundary surface. say create, you create your inlet, say okay. Okay, so this is your velocity magnitude. Okay. What you can do here is you can change it to geometric, show mesh. Okay. Now you go to streamlines, say create. Oh, sorry. Sorry. You go to streamlines, say put it scalar. Then you create velocity magnitude. Okay, 1 minute. I have not done very neatly. Delete. You create. Okay, I'll do it from first. Go to streamlines, create, change it to see the surface. The same way how I have done it for the pipe simulation. Select this face, say OK, then say calculate. Okay, then put it scalar, and most importantly put it local. So if you can see, these are the flow lines. Okay, so if I put spheres, okay, okay, you can change it to anything. So this completely depends on this. Okay, now if you want to see how the path is actually flowing from the car, what you can do is you can change the visibility off. You go here, you change visibility off. Uh, go here, you change it to show mesh, show mesh. Okay, now you can go to stream. What you can do is you can select create, you see the surface, you select this surface and say OK and say calculate. Okay, now change it to scalar. So you can see how the airflow is happening over from your car. Okay, so you can play with the number of seats to add. Okay, okay, Okay. 1 minute. Okay, so this is how I hope this is you wanted to see the path, right? I hope this is the one. Okay, so basically you can save this image, put it in a PPT and something like that. Okay, so I have shown you how to import your car model, how to do your volume meshing, how to create your mesh refinement zones, how to do your volume meshing, how to create your boundary layers, and then how to set up the boundary condition for aerodynamic analysis, and then how to do your compute your drag, and how to do your post processing. Okay, this is how you should do it. Then we will okay now most importantly, let us see. I will close this one. So aerodynamic analysis is over. Now let us go for exhaust system simulation. I do have a simple two-wheeler exhaust. It's a bike two-wheeler exhaust system. So I will import the CAD model first. So this is a two-wheeler exhaust system. Two-wheeler exhaust system, something like this. This will be connected to your engine part. The exhaust will come. This yellow color part is the porous medium. Okay, and this is your outlet. So sorry, this is your outlet. So basically, this is the porous medium. That it comes something like this. Okay, so how do we model this? See, anything, this thickness need not be mentioned. So the fluid touching the exhaust system is most important part. So you need to make sure that wherever the gases touch the exhaust system, you have to make sure that you capture only that part. Okay, so I have done exactly the same. So I'll delete this. I will import a NAS file, how I have done it, and show it to you. I'll open the ACS file for you before, because it takes some time to import. Okay, it's not closed. Okay, so so if you see, this is the meshing I have done. So if you see, I have closed this. This is my inlet. This is my. I have made sure that I have captured this part. This is the porous medium. The yellow part is my porous medium. There is a question. Sorry, I cannot. I think I have sent you. I can share the geometry file, but not the mesh files, because I need you to do it. Okay. So I think you can contact Apoorv for getting the geometry file of the same car. Okay. Then This is the porous medium, and this is the how the exhaust system meshing is there. This is the outlet. Okay, so let us go directly to the ACU console. So import this file. Uh, Import this file in the exhaust system in the ACU console. Okay, the NAS file, import it here, so it will come something like this. Now I have done the meshing part here as well. If you can see, that's a question, how to generate a cavity mesh from the CAD model. I didn't understand. So basically from the CAD, the pipe, I have already shown you how to import the geometry and how to do the meshing directly. So it is one and the same. You just need to do the volume mesh. It will generate the surface mesh and then do the volume mesh. Okay. Then if you can see, I'll say cut plane. Okay, so this is the volume mesh it has done. Sorry, it's a bit slow. Yeah. So can you see the volume mesh done here? So this is the volume mesh done. So can you see how fine the mesh has been captured here? That is why we have done this. Okay. So now let us go for the boundary conditions. Okay. This is an exhaust system analysis. Okay. So if you want to do an exhaust system analysis, you have to follow this procedure. This is very simple. So I have run maximum time steps of 3000 iterations. So if you see the surfaces model, go to volumes. There are a lot of volumes, separate volumes inside. Okay, so each what I'll do, I'll show you the volume manager. Okay, so all of them are fluid regions, which is air, and the porous medium. I have already told you the porous medium is just after the inlet. It has been given as porous. So this porous material model is something the customer normally the boundary conditions would be given. The customer would be given a boundary condition, something called as velocity versus pressure drop. Okay, so that you can directly enter here. So this is material model porous. So velocity versus pressure drop you can enter and it will calculate automatically. So this is the boundary conditions, one of the boundary conditions from the inlet to the outlet. So now let's go on the surfaces part. Okay, so you have to give your inlet outlet, and basically for the boundary conditions over the porous medium you need to give it as slip and rest of all as wall. Okay, and just you need to run the simulation. I'll show you the PPT of how the report has been done. So the objective here is to simulate the steady state CFD analysis of an exhaust system, then to calculate the velocity and pressure drop of the exhaust system, to compute the uniformity index. Uniformity index is computed exactly at 0.51 mm at the cut section of the porous medium. Uniformity index determines the flow uniformity. Basically, how the flow has been uniformly distributed over a cut section of the porous medium. Okay, so this is how whether the flow is flowing good or not, or the flow is stagnant over that period, has been located. So uniformity index plays an important role. This is normally called as flow uniformity as well. Okay, so this is an index where to see whether the flow is actually flowing very well over the cross-sectional area of a porous medium. Okay, so what are the basic CFD analysis steps followed? So prepare CAD model for CFD analysis, then build a surface mesh in hypermesh, then export the surface mesh in NAS format, then define this surface mesh and volumes, the boundary conditions basically, whether this is inflow, outflow, something like that, and then you need to make sure that you define properly the porous medium, velocity versus pressure drop, then define turbulence model. This is also SAE models, Palat-Almaraz, the same as the aerodynamic, whatever I have shown you. You can use the same turbulence model. Then we are doing a steady state analysis, not a transient analysis. So we do a steady state CFD analysis, and then CFD results post processing is done in field view. So this is the CAD model as I have shown to you, and the CFD model, the porous medium inlet outlet. So sectional view of the mesh. So you can see the 5 boundary layers over the porous medium. Then total node count is around 4,81,259. Total element count is 27 lakhs 25,429. So basically 2.7 million. Okay. So you can see the mesh over the porous medium, front view of the porous medium. So this is the porous medium boundary conditions. So I'll not spend much time on it because I don't think so you'll be doing a porous medium boundary condition, something like this. You can directly give directly Darcy multiplier function or Fourier-Selmer coefficient, sorry, Darcy coefficient or Fourier-Selmer coefficient, or you can give directly your velocity versus pressure drop. That is an input boundary condition. Okay, this is an input boundary condition, velocity versus pressure drop. So solver specifications. This is a steady state Navier-Stokes equation for momentum and continuity. Then we use a SAE turbulence model, that is Palat-Almaraz turbulence model. The convergence criteria is around 1e per minus 3. Eddy viscosity we normally give to initialize. For every simulations, wherever we use SAE turbulence model, you initialize the eddy viscosity to 1e per minus 5. Okay. This is the residual convergence. If you see, it has solved up to 20 time steps. Then the convergence for pressure and velocity have been converged, which is well below 0.0001. That is 1e per minus 3. So this is your Y plus model. So Y plus is a factor you should determine for the meshing. So you have to make sure that your Y plus is well below. So maximum Y plus goes up to 33. Okay. So these are the various cut section of flow happening. So from the inlet, from your right to left, if you can see, the velocity increases. Okay, that is how the velocity profile behaves over the cut section. Okay. So this is how the flow occurs. Okay. Now the flow uniformity index. Okay. If you can see here right now, when the flow gets into, there is a recirculation zone just before the porous medium. If you can see, so that should be avoided, so that the flow normally goes very good. So the optimization comes into picture here. So optimization of this exhaust system is done and then manufactured. So this recirculation needs to be avoided. Okay, this is how the flow will go, and basically the recirculation of these zones needs to be avoided. Okay. Flow uniformity, as I told you, plays an important role in measuring the compute uniformity, basically. Okay, so this is how the formula is used. So if you can see 2 mm section view at 2 mm before porous medium, it's around 0.782. We do have a script to measure the uniformity index over in AccuField view directly. So just let me know if you want to have those script. You can contact Apoorv for this, and I shall send it to him. So basically, if you want to see the porous medium uniformity index, there is a script where this formula is already been done. So you just need to read the script and you will get the UI value directly printed onto it. So this is section view at 1 mm. This is section view at the middle of the porous medium. You can see how uniformly the circulation has been done. It's around 0.897. Section view at 2 mm after porous medium. So this is the pressure drop of the complete system, that is inlet minus outlet. This is the pressure drop of the porous medium, 137 pascals. So computational time, it requires volume meshing with boundary layers 5, occurs to 10 minutes in a 4 GB RAM machine. Basically it is done in my laptop. So it generates around 2.7 million elements in 10 minutes. Okay. So we have a very good meshing as well as solving capability within our CFD solver, AccuSolve. So CFD solution, we took 36 CPU. It requires 15 to 20 minutes. So the conclusion, the pressure drop of the system is around 617 Pascal. The pressure drop of the porous medium is around 137 Pascal. The uniformity index at various cut sections have been shown. The UI value, of course, can be increased with the shape optimization. So we have a CFD optimization with AccuSolve and HyperStudy where you can change the shape and run the CFD simulation. Okay, so this is how the exhaust system CFD simulation is done. You can, Mr. Siddesh, you can contact Apoorv for the uploading of this recording. So basically, this session is being recorded, and you can contact Apoorv for this recording. Okay. So any questions? Please do type. So I'm just closing this. So we are coming to the last part now. Basically, disc brakes. So I will open, I don't have any PPT regarding this. So I will just showcase how the setup is being done. And then I'll video of how the disc brake actually works, how the temperature of the disc brake increases. Sorry. So basically, I've just done a disc brake. I'd say display on everything so you can be able to see it. So this is fixed. So basically, this is the ambient condition. Okay. See, if you have seen disc brakes, when we apply the brakes, there is a pad which makes sure that it gets attached to the disc, and the disc gets attached to the rim of the wheel, and your vehicle stops. Right? This is how disc brake works. So I have just concentrated on the pad and the disc. Okay, not on the rim of the wheel. So the disc and the brake and the normal disc, how the pad goes and stuck to the disc. So basically the friction occurs and the heat transfer between the pad and the disc occurs suddenly because it's rotating. Okay, so this is fluid fixed. This is fluid rotating. Basically, this is your disk. This is your solid fixed. So this is how this pad will go and attach to your rotating disk. Okay, and this will make sure that it generates some certain heat. Okay. So solid rotating. So basically there's a solid rotating. I have put it in a different collector. Okay. And it's very simple. Okay. So this is your disc brake which is rotating. There is a solid rotating and that's solid fixed. Okay. Now we go for the boundary condition. Problem description. This is a laminar problem. I've just kept laminar. You can keep this one. I'm interested in temperature equation, so I've kept advective diffuser. Okay. Then auto solution strategy. It's a transient problem. So I run it for see calculator. See maximum time steps 1000. Initial time increment 0.002. So 1000 into 0.002. Okay, it runs for 2 seconds. Okay, the simulation runs for 2 seconds. Okay. Then most importantly, this is not reference frame, this is a mesh motion. Mesh motion, we give rotation because this is rotating. The part is actually rotating. Then rotation center, you can go, okay, what I'll do will not be visible. You have to make it as transparency on. Okay, so this is your disk, okay, which is rotating. Then you go to your mesh motion. Then this is your rotation center. Say show. Can you see? So this is your rotation center, if you see. So exactly at the center of your rotating disk, the red color. Okay, that is your rotation center. Okay, so at what speed it is rotating? It is rotating at 100 RPM in y direction. Okay, it is rotating at 100 RPM at y direction. 100 revolutions per minute at y direction. Now you need to define the boundary conditions for the fluids. So fluid is normally air, so don't worry about it, the outer part. Then comes the fluid rotating. Fluid rotating is your blue part. So you have to make sure that you give mesh motion because that is the one which is rotating. Okay. Then comes solid, which is fixed. So this solid is made of aluminium. Then solid rotating. You also need to give solid rotating the mesh motion part and is made of iron. Okay. So it's very simple. You just need to make sure that you have separate volumes for this where you can assign certain boundary conditions. Let's go for surfaces. So there are a lot of surfaces. What I'll do is I'll just go to the surface manager. I'll show it to you. So normally the fluid wall is given and basically inflow outflow conditions over the ambient is given and symmetry boundary conditions has been given because it's rotating. Okay. So just run the simulation. You will get some certain results, something like this. If you can see the model, how the heat is generated, this is rotating, how the heat is generated you can see. So this is totally for 2 seconds. If you can see the time is 0.4, 0.5, 0.6, 0.8, 1 point and 1 point something and it gets stopped. So basically the convergence has occurred within the 2 seconds time limit. Okay, so you can see how the temperature gets generated when the pad hits the surface. So basically this is how the temperature gets generated. Okay, any questions? Any questions? I would encourage you to ask questions. Any questions do you have? Okay, that's a question. What is the green part? See, the green part here is the fluid rotating. This is the part. So basically you give air and you give mesh motion here. See, we normally define a volume over the rotating disk to make sure that, because the air also gets rotated over it. So we need to consider that. So that is how we model it. Any more questions? Any more questions? Okay, so I think there are no questions. So I would encourage you to do the CFD analysis for aerodynamic using AccuSolve. So I have covered the aerodynamic analysis of a car, stating how to do volume mesh, how to do boundary layers, how to do computation of drag, and how to post process your result using AccuField View. Then I have concentrated on the exhaust system CFD analysis. So exhaust system CFD analysis, how to compute the uniformity index, and how to do, basically how to use your AccuConsole for doing the same, and then the brake disk analysis. Okay, I hope that's one more question. Just wait a minute. Okay, what is the purpose of using mesh zone refinement? Basically, when you do zone refinement, the refinement word means that the mesh would be refined over that particular zone, whatever you create over the cart. So there will be a finer mesh apart from your wind tunnel when you create that mesh zone refinements. Okay. Any more questions? So there is a so any queries you have, you kindly send it to this email ID on the screen. So any queries you have, you send it to educationsupport@india.altai.com. So one of our engineers would help you in all your queries, whatever you have. Okay. So any questions? Okay. So I think we have come to the end part of our CFD training over the aerodynamics, exhaust system, and disc brake analysis. So any queries, any further queries you have, please contact the mail ID on the screen. We shall help you. So have a nice day, all of you. Thank you for attending the AccuSolve CFD training session with Altai. Thank you.